Deborah! I know you're in there. It's Annie. Deborah? Answer the door. Deborah!
I think she's very crazy, absolutely wild, mad woman. Does strange things all the time.
Joyce! It's Annie.
We went on holiday to Alaska, and that was where it all started.
I'll make you rich and famous.
Annie Taylor is on a mission, fired by a glittering dream. Every weekend, whatever the weather, she drives to the special secret places where one day the chemistry of nature could make her dream come true.
My friends think I am totally bananas. They can't understand why I want to stand out here in the cold in the river on my own. They just think I'm balmy, I think. I went to Alaska in 1994, just for a holiday, basically. And of course, as soon as you get to Alaska, the first thing you see is people wearing great big nuggets of gold and visits to gold mines, gold camps, try your hand at panning. So I thought, oh, I'll have a go at that. And that's where I got the bug, basically. I couldn't really believe that there was still gold in England and Scotland that was worth going out to look for. But I thought I'd give it a try. I just love it. I love it.
Human beings have always valued gold, not just because it's rare, but also for its physical properties. Gold doesn't corrode. If you know where to look in the landscape, it's one of the few chemical elements you can find in its pure form. But the reason why you can find pure gold, and the reasons why gold is so precious, are buried in another landscape, the chemical landscape of the periodic table. Here are all the known chemical elements in the universe. Chemists have put them on a roadmap, an A to Z of the most basic materials known to science. It's the key to chemistry.
I like to think of the periodic table as a country to visit, that you can imagine flying into it, just like you fly into any country as you go away on holiday. As you fly into it on the left, you will see these great plains of shining metals. But as you fly over towards the right-hand side of the periodic table, then the landscape gets much, much softer. Here are the non-metals. Many of them are coloured. Some of them are liquids. So we fly over regions that may be green, that may be brown, that may be black. And we see below us two lakes.
Bromine is a brown liquid at room temperature. The other lake is more familiar. Dental fillings and thermometers traditionally use the shiny metal mercury. Next door is gold.
Gold is a great place to go. It's probably one of the best holiday spots in the whole of the periodic table. I mean, it looks nice. It looks as though you're standing on this brilliant yellow beach. And you're surrounded, well, on one side of you, there is actually a sea. There is this liquid, shining, silvery mercury, which are lapping at the shore.
Mercury is very unusual. It's the only metal which is liquid at room temperature. The other metals dominate the periodic table. Virtually all of them are silvery grey.
The long skinny bit in the middle of the periodic kingdom, which, well, chemists don't call it the long skinny bit, they call it the transition metals, is really interesting because in a sense it captures the progress of civilization. If you start on the far right. Copper and zinc were the metals that were used for the Bronze Age. And as you gradually walk your way towards the left, you come to iron, which of course was the later Iron Age. If you go further across still, you get to elements like titanium. And of course, titanium is the material that makes space travel possible, light and strong and durable.
The elements are special because everyone is made from a different kind of atom, just that one kind of atom. Every element has its own special properties, but sometimes those properties are shared by a family of elements. The periodic table groups these families together. The horizontal rows of elements are called periods. The elements along one seem quite different, but look up and down a group of elements and they seem to be quite similar. Understand the characteristics of a group and you get a handle on the behaviour of all the elements in that group. Here's lithium, a soft grey metal. Below it is sodium, softer still. Like all the elements in group 1, they share similar properties. Across the whole periodic table, a picture emerges which can reveal hidden secrets in nature. The best way to find an element is to know its physical characteristics. Panning for gold works because gold is so heavy.
You usually put about 4 or 5 pumpfuls into the pan. That way, it doesn't hurt your back when you bend down. It's usually sufficient to work with. It's about 1 kilo of gravel. And what you're doing in the pan at this point is actually what the river does naturally. It's taking the heavy material to the bottom and the little pebbles come off the top. And as long as you remember that you need to use the right sort of movements and keep thinking about the bottom corner of the pan, which is the bottom half of the circle, then the gold will naturally go to that point. Yes, I found a bit, little tiny piece, but it's so tiny I think we'll pop it back until it grows up. I would like to get enough gold to make a ring, that's my ambition. There is a good jeweller near where I live called Craig MacLeod, who is a craftsman, and he will actually make a ring to any design with the gold that I collect. So I'm hoping eventually to have myself a nice ring made.
From melting the nugget, you end up with a small bar. You roll the bar out to this shape, so you have the width and then the depth of the ring you want. And then it's curled round into a ring and soldered.
Gold is so soft that it bends easily by hand. And a steel saw will cut it because steel is harder than gold. But steel is not an element. It's a mixture of iron, carbon, and elements like chromium.
That's the ring itself actually soldered together. And from now it'll be polished, it'll be filed and polished and made into a piece of jewellery.
For thousands of years, craftsmen and women have chosen gold to make jewellery, not just because it's rare, but also because it can be drawn into fine wires or beaten into thin sheets. These physical properties are shared by other elements in the same group of the periodic table as gold. No surprise then that silver and copper also make fine jewellery. There are 4 times as many metals in the periodic table as non-metals. In another of the table's patterns, The non-metals are clustered in the top right-hand corner.
There are a bunch of elements close to the right-hand side of the periodic table and near the top that are important in life. These are the elements of life. And they're elements like carbon, nitrogen, oxygen, and so on. And there's an enormous chemistry that's obviously very important because it's all around us and it's inside us. It's the chemistry that actually produces life on Earth. And one of the important things about these elements is their ability to form bonds with themselves, particularly carbon is able to form chains of molecules. And these chains of molecules elaborate a little bit with other elements like oxygen and nitrogen and so on, are actually the elements that form molecules like DNA.
It's possible that elsewhere in the universe life exists based on elements other than carbon. But we wouldn't be the same without it. Plants, animals, and the whole of the natural kingdom depend on the chemistry of these non-metallic elements.
I like gold because it is a natural, beautiful metal. If it's a good day, I would come up here and I would spend 12 hours on the river in the summer. On a bad day, I'd spend about 8 hours in the river. So over the years, it adds up to quite a few hours. I find it very therapeutic. I think it's getting away from the city. No telephones, no pressures, no stress. And this place is beautiful. Absolutely lovely. Plus you can find some gold. Excellent. Can you see that? That is gold.
Most metals aren't found in their pure state in nature. Instead, they're chemically combined with other elements. To extract and turn them into useful metal, elements like iron have to be forced to give up their natural chemical partners, using heat in a process called smelting. Iron is quite reactive, so it rusts quickly in water, but other metals react even faster. This is cesium. Cesium is in group 1, a group of highly reactive metals.
If you thought of yourself walking down this group of the periodic table and it was raining on you, then it would be the most dramatic sight in the world, and it would be really dangerous. The metals at the beginning of your walk, like lithium and sodium, would react with the rain and you'd get hydrogen. But by the time you got down as far as rubidium and cesium, the intensely reactive metals at the bottom of the group, at the end of your walk, then you wouldn't survive. I mean, they would simply explode every time a drop of water touched them.
In this model, the most reactive elements are shown the tallest. Group 1 elements sit at one peak of reactivity, but way across at the far side, elements in another group are just as keen to react. Here is group 7.
If you were to start at fluorine, well, you wouldn't get very far. I mean, that really is the most reactive gas in the periodic table. And indeed, it took ages for chemists actually to isolate it because it was so reactive. Suppose that you got round that problem and put yourself in a spacesuit that enabled you to survive. You would actually see a very interesting countryside as you walked down the group. You would see fluorine as this rather delicately pale green, almost colourless gas. Then you go into a region of slightly darker colour, greenish yellow chlorine. Then you come to really a deep brownish red lake, bromine. And then on the other shore of that lake there is purple, violet, black crystals of iodine. It really is a very beautiful walk to take. It's the most colourful part of the periodic kingdom.
Colourful, but highly reactive. Group 7 elements are dangerous to humans. During the First World War, chlorine gas was used as a weapon. It reacted with the water in soldiers' eyes to form bleach and hydrochloric acid. Thousands were blinded. The reason chlorine was such a horrific weapon is locked inside its atoms. Every atom of chlorine is the same. A cloud of electrons surrounds a central nucleus. The electrons carry a negative electric charge. But right in the middle, the nucleus is positive, because it contains a number of positive particles called protons. Also in the nucleus are neutrons, but they play only a small role in chemistry. Most of chemistry is about what happens outside the nucleus, what happens to the electrons. If it were possible to see an atom using a microscope, this is what one might look like. Squashed flat, the electron cloud would look like a set of rings called shells. 2 electrons are all it takes to fill the inner shell, but the next one out can hold up to 8. In chlorine it's filled, but the third shell isn't. Again, it's got room for 8, but with only 7 spaces occupied, chlorine has a gap which it is desperate to fill, and that's why it is so reactive. The goal of every element is to fill its outer shell of electrons. But one group of elements has already got there, Group 8, on the far right of the periodic table.
Really, there's not much to see here, and very little going on. These are the so-called noble gases. Right at the bottom we have radon. Not much is known about radon, except that it's intensely radioactive, which is why people don't like to investigate its properties. A bit further up you get to gases like xenon and krypton, argon and neon. These are gases that are used in advertising signs and in lasers and so on. But they were once called the inert gases because chemists, when they were first discovered, thought that they simply didn't react at all.
Now we know that's not always true. But the Group 8 gases still hide away in the periodic table because they're so unreactive. Their next-door neighbours, Group 7, are desperate to react because they only need 1 more electron to be stable. But on the opposite side of the table, Group 1 metals have the opposite problem. 1 electron too many.
The key property of the chemistry of all of these elements is that they're all desperate to give up 1 electron. And once they've given up that single electron, then they're in a nice stable form. And that's where they want to be. But the other point is that lithium might be pretty desperate to give up its electron. Sodium's even more desperate, and potassium is more desperate still. So as you go down the group, you can predict in a systematic way the way that the element's going to react on how desperate it's going to be to get rid of its electron.
Most metals are more than happy to react with elements like oxygen in the air, so they corrode with time. But not gold. It keeps its sparkle because of its chemical properties. That's what makes it so precious.
Oh my God, look at this. Look, 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 look. Look. Have you ever